Okay, good morning, everybody. Really appreciate everyone. I think it looks like there are about 48 of you. I appreciate you all being on time. And I thought I was going to be in an empty classroom when I came at 8:15 to get set up. So shows, I hope, that you're excited to take this course this term, or at least just to get out of the heat for a little bit. This is a great room, but one of the unfortunate things about it is it's going to be very hot this week. There's I don't even think those things work. The ducts at the back are for heating only, and the heating might actually be on in the morning if it's 20 degrees or less. So it'll get better, it'll get cooler, so just hang tight, but otherwise it's a fantastic room to be in. Just so everyone knows, I'm making an attempt to record all of these lectures. That way, at least if you're not able to come to class, or you're able to come to class and there's something that you forgot about and want to review again, I'm hoping it works out. This is the first time I'm doing it as kind of an elaborate setup, but I trust that it's going to work out okay. But just know that if I'm walking near you and you say something, it might be caught in perpetuity on the internet. So just when I'm near you, just make sure you're not saying anything kind of weird or strange. So welcome to CE 3063. It's probably, for many of you, the first and only course that you're going to take on the design of steel structures. I say the first and only for some of you because maybe not all of you are interested in structural engineering courses. But for those of you who do want to be a structural engineer one day, there is a second follow-up course to this called CE 5063, which is Structural Steel Design 2. All right, my name's Taylor Steele. I'm going to be the instructor for this course this term. This is my second time teaching the course, so even though I don't think I look that young anymore, but I do expect that this is going to be a fantastic experience for everybody. I really enjoy teaching this course, and I think that whether or not you want to be a structural engineer, I think everyone's going to get a lot out of this course one way or the other. Before we get too deep into the stuff, I'm going to introduce the course to you all today, but I just want to get a sort of sense for where everyone is coming to this course from today. I'm the first green dot there. I'm from Truro, Nova Scotia originally, though I did come to UNB to do my undergraduate degree. For those of you who are familiar with Poll Everywhere but don't see the login information up here, there are two ways to sign in. You can go to polleb.com/steeldesign. You can do it on your laptop. You can do it on your mobile phone if you text Steel Design to 37607. 37607. And I've also included a link to the Poll Everywhere sessions for this course on D2L. So if you go to D2L, there should be a widget on the course homepage that you click, and that should take you directly to Poll Everywhere as well. But I'm going to be doing this at least once a lecture, and so I recommend that you go to this link today and bookmark it so that you can easily access it later. Or if you're texting on your phone, it should just maintain that text number for you, and you don't have to do anything beyond that. So there are a few options. I've got the Maritime Provinces up here, and that's not to be exclusive, but it's just so that I can see some cities up here. And I understand that most people do generally come from the Maritime Provinces, though sometimes we get some folks from other provinces and other countries as well, depending on the makeup that year. So we got a couple folks from another province, one folk from another country. Who's from Cape Breton, if you don't mind me asking? Welcome. We'll give everybody maybe another few seconds here just to get in and sign on. If you don't get in to sign on and do this one, that's fine. These are never going to be a graded component of the course. It's just to try and get a little bit more engagement with you guys, and I want to also, throughout the term, as we get into some of the lecture material, gauge your understanding through some Poll Everywhere questions similar to this one. So it seems like we got a lot of folks from New Brunswick, St. John in particular. We always get a lot of folks from St. John, Fredericton, Moncton, a few in between. Who's from PEI, if you don't mind me asking? Awesome. What brought you to you? And did you go to UPEI first, or did you come straight here? Straight here. Straight here? Awesome. And who's from another province? Is somebody outside of New Brunswick? All in one spot. Where are you all from?
I live in Alberta.
Alberta? Nice. Welcome. Newfoundland? Quebec. I almost got you two in there, but I was nowhere near getting Alberta in there. Yeah.
I came out here originally from BC and then went to UNB St. John for 2 years.
Okay. Awesome. Are you? So.
I didn't notice that option.
Okay. Perfect. Yeah. Fantastic. Is anyone here from another province? Yep. Ontario? Awesome. I spent 5 years in Ontario when I was doing my PhD in McMaster at Hamilton. Anybody else from outside of New Brunswick? And there's one, I don't know what this is. This other country? Is someone not from Canada here today? Yeah? And you're from? China. China. Welcome. South Africa, interesting, welcome. Yeah. Egypt. I know a lot of people from Egypt. A lot of people from Egypt go to different schools in Canada, particularly for grad school. So welcome, thanks for coming for your undergrad degree here. Anybody else that I missed from outside of the mix there? Yep. Bahamas. Ah, welcome. It's probably warmer in here than it is in the Bahamas most days, eh? All right. No, that's fantastic. And I appreciate everyone participating there. I'm going to do this quite often. So again, bookmark this link so that you have it at the ready. So we're going to be doing activities like this quite often throughout the course. So this is just, I didn't print a syllabus or a course outline for everyone because I wanted to save 500 sheets of paper if I could, but I distributed the outline by email to everybody. The other reason I didn't print it out is because it's going to change a lot. I make a lot of mistakes in documents like that, and so as things change, I'm going to update the live copy on D2L, so I don't want anybody to have an old version of the outline sitting around that they're referring to when the proper updated copy is on D2L. Okay, but all I really want to do today is introduce what the course is going to be, get everyone excited for structural engineering, even if it's the subject that you like the least. Because I do believe that this is overall going to be a positive experience for everyone. This is really something that I enjoy. I practiced as a structural engineer for 4 years before joining UNB. And so steel design is something that's really close to my heart and something that I hope that I share with you all through my enthusiasm for the course material. I want to start by showing some steel buildings that were recently built locally here in Fredericton. This is on the north side. It's a middle school. I'm pretty sure it's a middle school that MBDTI owns. And so generally you can see it's a 2-story building. It's pretty big in footprint. It's quite wide because there's a lot of space to develop on the north side. But this is just one example of a steel frame building. And generally what you see oftentimes with steel framing is to start constructing the building envelope, they start to use other materials like masonry to infill, basically close the exterior walls around the outside of the building. I don't know if this is finished. I doubt it's finished because most projects are not finished when you think they'll be. But this was the state the building was in this summer when I went to take a visit with NBDTI and grab some photos that I'm going to use throughout the course. Most exciting project in Fredericton right now, I think everyone's seen it. Put your hand up if you haven't seen this building downtown Fredericton. So if you haven't seen it, it's pretty easy. If you ever walk downtown, you'll see it, right? It's right at the corner of King Street and Regent Street. This is the new Justice Building, or the new courthouse that they're building downtown in Fredericton. It's the tallest building, I believe, that we'll have in Fredericton once it's completed. It's only 6 stories, but because courthouse floors have to be so tall, they generally have to be 6 meters tall, it's going to be the rough equivalent of a 10 or 11-story building downtown Fredericton when it's finished. Okay, so I do hope, this was the state that was in maybe, I think it was July when I took that photo. I took the technical elective class downtown to see this building in the winter term last year. As you can tell, if you've seen it, it's still not getting closed up yet, and I think it's going to be that way for a while. So I do hope that we're able to go and actually see that building. I'll take you through some of the components that we're going to be talking about in this course. But that's a really exciting building, and it's definitely a mega project when we're considering what we do typically build in Fredericton. So before we get too much further, I just want to get a little bit of input from what y'all are thinking. What do you think about when you hear structural engineering? I really want to know what you guys are thinking about structural engineering when you come to this course. It can be how it makes you feel. It can be things that you think about. It can be a structural system, whatever you want to put up there in terms of a word. And basically what's going to happen is the words that get repeated the most are going to get bigger. And so we're going to see some commonality in terms of the different types of things that you're all thinking. So obviously we're seeing bridges come up a lot. That's definitely a type of structure that people think of a lot when they think of civil engineering, let alone structural engineering. Design, that's specifically what this course is going to be about. And it's going to be the first structural design course that you have at UNB, the structural steel design class. Framework, buildings. This course is primarily going to be about buildings. And so when we're talking about the design of components, we're not going to be talking about bridges or the random other structures you see. We're primarily going to be talking about the design of building systems in this course. Statics, I hope everyone's familiar with their statics. And if you're not, we're going to go through some exercises later on the course to make sure everyone's up to speed. But liability, that's a fantastic one. And we're going to come up to another activity in a little bit, but liability is a big part of a structural engineer's professional responsibilities. Anything a structural engineer designs, they're liable for, right, in terms of the performance, in terms of the safety, which I saw up there. These are all great words, and it seems like everyone's generally in the right mindset for this course. I just want to give a couple of, definitions that folks have come up with over the years. There are two kind of contrasting definitions. The first one comes from the Institute of Structural Engineers, which is an institution in the UK that handles structural engineering similar to the way that APEG and B would handle structural engineering or the practice of engineering in general in the province. And that's that structural engineering is the science and art. Note those two things together. It's an applied science course, but there's a certain art that comes with structural engineering as well. Knowing how to make things look good, that generally comes with practice. The art of designing and making with economy and elegance. That's another thing, economy and elegance. One famous saying about engineers is that engineer can do what any fool can do for $10 for one. And so economy is a big part of what we do as structural engineers. We don't want to make things and design things that are going to be too expensive. Buildings, bridges, and frameworks and other similar structures so that they can safely resist the forces to which they may be subjected. So basically what it is to be a structural engineer is you're working with usually architects and some other folks and the owners. They've got an idea in their head of what they want to do. The architect has big ideas of what they want to do, and part of your job is to make it work, essentially, when it comes to buildings, bridges, frameworks, and other similar structures. This is a very noble definition of structural engineering. It makes you feel like you're doing something grand and that you've truly got the experience and practice to be able to meet the definition shown here. I really like this other definition, and that is that structural engineering is the art of molding materials we don't really understand into shapes we can't really analyze, so as to withstand forces we can't really assess in such a way that the public does not really suspect. And that's kind of a pessimistic definition of structural engineering. It's like, well, we don't really know what we're doing, but we've done it and it's worked, and no one's the wiser, so to speak. And so we're going to talk about each of these three things. We're going to talk about, well, four things, I suppose. We're going to talk about the materials, right? What material is. We're going to talk about the properties that we use as engineers to define steel material. And that's why we say we don't really understand it, because if you took materials engineering, material science for engineers, you talk about cubic crystal structure and all these fancy scientific terms that we never think about anymore. We don't really understand what they are when we're just sort of quantifying the response the best we can. And the shapes we can't really analyze. We're going to talk about the different shapes that steel gets rolled into to make different structural elements that we use to build structures. And from statics and mechanics, we mostly know how we can probably calculate the stress on some of those sections, but it's theoretical. Sometimes it lines up with experiments, sometimes it doesn't. So sometimes we can analyze them, and sometimes we need a little bit more skill to do so. So as to withstand forces we can't really assess, we're going to talk about how engineers are given certain prescriptive requirements for calculating loads. We never know exactly what the load's going to be ever. It's very difficult, and there's a whole science behind calculating loads. And the reality is loads are always going to be different in time. So we can't really assess them, but we do the best that we can to make sure that all of our structures are safe enough so that the public can use our structures safely, that they use them in a way that isn't annoying to them, and that they enjoy using the infrastructure that we build for them. So I see some folks have already gone into this activity. I just want to know in this course, of the cross-section of students that we have here today, just select the thing that best reflects your current position. There's, I definitely want to be a structural engineer. I might want to be a structural engineer. I don't think I want to be a structural engineer. And then for everybody else, I definitely don't want to be a structural engineer. All right, and I'm actually going to go put my answer as well. Put your hand up if you definitely want to be a structural engineer, if you're comfortable doing so. That's about right, typical, 10%. For those of you who might want to be a structural engineer, what's holding you back, if I might ask somebody who wants to share?
Not sure
Unsure of options?
Yeah, really big liability.
The liability, yeah. I'll share with you my answer. My answer was I definitely don't want to be a structural engineer. And I'm saying that a little bit to be a bit provocative because I'm a structural engineer and I've been a structural engineer. But I stopped being a practicing structural engineer for a reason. And the reason was the liability, the stress. It is a tough job. And you've got to have the strength of character, the professionalism, and really thick skin because you take a lot of shit as a structural engineer. You take a lot of risk, and no one's going to be a multimillionaire as a structural engineer. If you love it and you want to contribute to your profession every day, go ahead and do it. That's what I wanted to be for a while. I came to the university because I love to teach structural engineers. I want to teach people to be structural engineers. Okay, so anyway, that's a pretty good exercise. I'm pretty pleased with this overall, and I'm hoping that over time, maybe I'll do this again at the end of the term, maybe we get some folks shifting towards the left, maybe we get some folks shifting towards the right. We'll see what that's like over time. For those of you who do want to be a structural engineer, or you think you might want to be a structural engineer, this is the roadmap to how you should approach your education at UNB to achieve those goals. Until now, we all should have successfully completed statics, mechanics of materials, and structural analysis. And I hope no one's forgot about those because they're all going to be very important in this course. And they're also going to be important for every other course that you take in structural engineering. There's reinforced concrete design in the winter that everyone has to take as well. And then in general, we offer 3 technical electives at the 4th year level. Structural engineering, which is with CAVE, but it's a very important course in structural engineering, and I hope he continues to offer it. You basically learn to program a structural analysis software using the direct stiffness matrix method that you learned in 2033, for those of you who can recall what the direct stiffness method is. You're going to take structural steel design 2 with me again. If you enjoy this course enough, you might never take that course with me, but I hope you do. And reinforced concrete design 2, so you can kind of see a pattern here. Right, you get the foundations of how statics works, how stuff starts to move, and how things are strong. And then you do structural analysis essentially twice, steel design essentially twice, reinforced concrete design essentially twice. And Tom Joyce, a new teaching professor here, might teach a course on structural timber design for those of you interested in wood buildings. Okay? So obviously these 3 courses are very, very important. You don't have to be an expert in those courses to do well in this course. But you can't have gone through these courses retaining no information and expect to succeed in these courses hereafter, okay? And so basically what I mean is you should already be able to do these things before you come into this course. You should be able to calculate the axial forces in members forming statically, and determinate is okay. Statically determinate trusses. If there's anything indeterminate, we'll use a structural analysis software. But you should be able to do method of joints, method of sections relatively quickly. You should be able to draw shear and bending moment diagrams for determinate or indeterminate beams. And again, we're really just going to look at determinate beams in this course. There's a saying, Professor Michael Collins at U of T always says, in first year we teach civil engineers to draw shear and bending moment diagrams. In the second year we teach students how to draw shear and bending moment diagrams. In the third year we teach them how to draw shear and bending moment diagrams. And in the 4th year, because it's pretty important, we teach them how to draw shear and bending moment diagrams. If there's nothing you can do other than draw shear and bending moment diagrams by the time you leave this program, you're probably going to be okay. All right? Can't emphasize that enough. Should be able to calculate the elastic deflections of determinate trusses and beams. Again, mostly beams. We're not really going to look at the deflection of trusses that much in the course, but that's a tool that you should be familiar with and able to do. Describe the material properties of ductile metals. Steel is, as we'll see later on, a very ductile metal. You've taken mechanics of materials and material science, where you've done tensile tests of steel coupons. You understand generally what the difference between ductile and brittle is. You should be able to calculate axial bending and shear stresses in elastic beams. That's your MC over I, your P over A, TC over J, those kinds of stresses in elements. And you should be able to calculate the average shear stress on pins, bolts, and single or double shear. I hope that everyone remembers the difference between single and double shear. If not, I'll discuss it, but that's usually one of the things in mechanics of materials that doesn't go super well. But we're going to be revisiting the single and double shear, especially when it comes to the strengths of bolts that we use to connect our steel structures together. The reason why these tools are so important, we're going to be looking at structures similar to this one. And you might say, okay, well, it's a building and I just need to design the steel elements. But in order to figure out how big all of these braces should be, for example, and how big these columns should be, for example, you have to do a structural analysis. And in general, it's pretty common for us to go through and simplify some of these structural systems in our buildings using simplified approximations. And so we might be able to say, okay, I'm going to replace this braced frame, as we call it in the steel structure, with a truss. And I'm just going to analyze it as if it was a truss with pins at all the ends, and I'm going to calculate the axial forces using either the method of joints or method of sections. We're going to need to be able to do that to get the axial, tensile, or compressive forces on our braces, and then we're going to talk about how to design the members for those forces. Beams and columns. We see a floor system here. We've got some smaller beams supporting a steel deck. Those smaller beams are supported by, in housing terms residentially, main carrying beam, some folks might say, but we're going to call it a girder in this course. And then all that is supported by a post that sits on the foundation at the bottom, and we're going to call the posts columns in this course. All right, so each of those individual elements is something that you've already seen before. We've got some beams carrying uniformly distributed loads, one of the easiest cases to analyze of all the static problems that you've tackled. Those uniformly distributed loaded beams are going to sit on the girder, and those reactions from the joists are going to cause actions on the girders. You've got a series of point loads on a beam. You should be able to draw the shear and bend and moment diagram for that case, and you should be able to calculate what the deflections of those beams are going to be vertically. All the loads from some of the joists and some of the girders are going to be supported by the columns. And so when we calculate the reactions in those members, that's going to be the action or the axial force on the columns. And so we need to understand how the pieces work, but we also need to understand how all those pieces fit together if we're going to figure out how the loads get from the floor down to the foundation. And that's a key part of structural engineering, is not just understanding how the components work, but how they work together to form a structural system. We're going to talk a lot about the design process in this course because obviously we're designing things. In general, this is a very high level view of what the structural design process is. We're going to start with planning, and that's usually done in conjunction with the building owner, the architect, some trades folks, maybe the general contractor gets involved a little bit if they've got some folks that they haven't engaged yet. What are we going to build? That's the planning stage. Preliminary framing and plans and elevations, basically somebody needs to say, okay, what are we going to build? How do we think we're going to build it? And that generally comes down to input from the architect and the structural engineer. Sometimes the mechanical systems, or if it's an industrial system, oftentimes buildings are built around the process. And so if you've got heavy industrial facilities like you've got in St. John, for example, you build a building around the equipment and the process machinery that's making the things that they're trying to make. And so sometimes it's in collaboration with the process engineer. Once we know how we're roughly going to build it, now it's the structural engineer's job to calculate the loads in accordance with the National Building Code of Canada. Based on the loads, we're going to do a structural analysis to figure out the load effects on those elements. And then once we know how much force each of those things are going to carry, we're going to perform a member selection or specification in accordance with the Structural Steel Design Standard CSA S16. At the end, you come back and say, does this work? Is this economical? Is this meeting the performance expectations that the client has for this building? And if not, you iterate. You go back and say, can I move these columns? Can I play with the spacing? Should I go with 2 beams here instead of 3? And those are the types of iterative decisions that structural engineers are responsible for making throughout the design process. Eventually, you're going to land on something and say, okay, we're happy, the client's happy. We're going to prepare final design drawings that essentially the owner's going to take. They're going to give it to a general contractor and say, build this for me and tell me how much it's going to cost. And then throughout the construction process, the contractor is going to be responsible for retaining some professionals to document what happens on site, especially if they built something differently than what was planned. It happens often. You run into issues in the field, they're trying to build something, and it doesn't work out the way that they thought, so they make a change in the field, and you have to document that. And sometimes the engineer will take responsibility for it, sometimes they won't, and it depends on what the firm's risk tolerances, essentially. But we can't forget about a very important part, which is people have to use this building every day. People have to maintain this building every day. So even after the building's constructed and it's occupied for the first time, engineers are still thinking about, okay, is it comfortable? Are the floors too bouncy? Are the braces shaking too much? Is there too much noise? Is the wind blowing the building so much that people are uncomfortable? And did I select materials that are durable enough so that this building is going to perform as intended for its 50-year lifespan? Okay, so those are the things that we think about throughout the structural design process. So the structural engineers are primarily engaged in this stage, but they're stakeholders in the long-term performance of that building as well. When it comes to building stuff, generally there's someone who wants to build something, and they're usually the owner, or in engineering terms, the client. Usually the owner, like at MBDTI, for example, they've got an engineering department that looks after engaging different design firms to do the design. They're responsible for engaging the contractors to do the construction. And so oftentimes what happens is the engineering department for the owner is going to say, okay, we need an engineering team, and we need someone to build this. They ask for proposals from different engineering consultants, hoping to get the lowest price on design. Generally, in the engineering consultant, you've got the lead engineer. And if we're talking about structural engineers in general in this course, you've got the lead structural engineer who is ultimately going to stamp the drawings and take that liability for the design for the 50-year lifespan of the building. Generally, the lead engineer has a team of design engineers supporting that mission. Maybe somebody does some of the foundations, somebody does some of the steel work. One of the jokes when we're doing high-rise design is you got the beam engineer, the column engineer, and the foundation engineer. And they do what, someone's really good at designing beams, someone's really good at designing columns, someone's really good at designing foundations. But ultimately, there's one person who's going to take responsibility for all that work. The goal of the engineering design process is to generate design documents that can be issued for construction, IFC, that the client can take and say, these are a set of plans that you can build me something from. Engineering department's going to take that set of design drawings and say, contractors out there, I want pricing to build this for me. And they're going to say, who's going to give me the best price? Who's the best suited to do that thing? And under the general contractor, they generally get different trades involved. They get subcontractors. But on the steel side specifically, you're going to get the steel fabricators and erectors like Ocean Steel. They're the ones who are responsible for all the steel work at the Justice Building downtown. NBDTI said, or the general contractor said, we're going to get Ocean Steel to do the steel fabrication and erection for us. And then you've got procurement. They've got to get materials to site, subcontractors for material finishing, carpentry, mechanical, plumbing, HVAC, all that stuff. And they're responsible for construction documents, documenting what happens in the field, making sure that what is built reflects what happened in the design drawings, and documenting any changes that occur along the way. One of the things that misses a lot, and I just want to get you all aware of now, is what's the communication line between the engineering consultant and the general contractor? What do you think would be a good communication line between the engineer and the contractor? A project manager on both sides, perhaps, and they talk directly, right? Wouldn't that make sense? Contractor saying, oh, I've got all these issues, and they're going to talk to the engineer directly. That's not what happens usually. The main line of communication is general contractor has a question. They submit the question to the engineering department of the owner. Maybe the engineering department takes it to the owner if it's a serious issue that's going to have financial implications or schedule implications. And then the engineering department is going to go to the engineering consultant and say the contractors have this problem or this question. And so it's kind of this back and forth process. Questions rarely get answered on the first time. But that's something that ultimately we end up dealing with. And the worst part is that under the general contractor, your steel fabricators and erectors, they're actually the ones who are responsible for designing parts of the structure. The lead consultant, the lead engineer, is responsible for designing the beams, columns, braces, et cetera, in the building. But how everything fits together and how everything gets connected is actually the responsibility of the fabricator erector. And so there's some engineering happening long after the engineering happens, and they're three arms of communication away from, making those things work. And so we're going to talk a little bit about how the engineering consultant can make the connection designer's job easier and minimize some of those questions that come back up throughout this course. Anybody have any experience using the NBCC yet? On a technical side, like, what's your, yeah, yeah. Other folks? Liam, I know you do. Yeah. Okay, perfect. Like a structural side or like residential side or? Yeah, residential. Okay, perfect. Anyone here? Yeah? House construction. So the Part 9 stuff, like this is big enough and that's big enough and that's done right and this is done right. The NBCC is a big document. And in fact, it's not even technically a legal document as such. The NBCC is what's called a model code, which is something that some smart people in Canada get together and think this is probably the right thing to do. And they put that as a requirement in the building code. But the building code is a federal document, and construction and engineering is not legislated at the federal level. It's legislated at the provincial level. And so it's the province's responsibility to either accept or modify the NBCC in a way that it works for the province. And so in New Brunswick, for example, because we're poor and don't have a lot of budget, we just say we accept NBCC as it is. And so right now, though, even though the NBCC 2020 is a document that exists at the federal level, we don't use NBCC 2020. February 1st of 2021, the New Brunswick government legislated the adoption of the 2015 version of the National Building Code for the province. All right, so, but what this does is it's a document that gives design requirements, construction requirements, and use requirements for buildings. Not bridges, not signposts, no other structures, but buildings that people meet in. And that's all the NBCC is for. Some people try to use the NBCC for other things. Don't do that. If you're designing a building, use the NBCC. It's literally called the National Building Code. And that doesn't mean building something. It means a building. Along with the NBCC, there's a part that we care about most in this class compared to others, and that's Part 4 of Division B. And that's mandates structural design. If there's something non-residential that requires a structural engineer, the structural engineer has to make sure that the building is going to meet Part 4. Part 4 tells us how to calculate dead loads, live loads, wind loads, snow loads, and earthquake loads. And we'll talk about most of those throughout the course. The other thing the building code does is it refers to material design standards. This is a structural steel design course. Steel is a material. NBCC doesn't tell you how to design with structural steel. It tells you what document to use to design with structural steel. And so the NBCC 2015 references the steel design standard called S16 from the year 2014. So right now in New Brunswick, you use NBCC 2015 and CSA S1614. Some people use 15 with 19. Don't do that. Don't use 9 because 9 is formally withdrawn and you'll get in a lot of trouble for using 9. In this course, though, because in the next few years, by the time you graduate, it's likely that NBCC 2020 is going to be adopted. NBCC 2020 refers to S1619, and so in this course, we're going to be using 2020 and S1619. And it's similar enough. It's not significantly different from the other versions because things change incrementally over time. But every 5 years, things change. We're going to be focusing on these two documents in this course. This is what S1619 looks like. Again, 14 is current-ish, which means that's what we use in New Brunswick. Again, it's referred to in the building code. And what this document says is how the structure must be designed to resist the loads that are prescribed in the NBCC. So these two documents go hand in hand, right? NBCC is freely available now. You used to have to put a copy on the reserves at the library or pay like $600 for it. Now it's a PDF. There's a link to it in the widget on the homepage for this course. You click the NBCC link and you'll go right to the document. S1619 is available online at the UNB libraries for free. It's also part of the handbook. We're going to talk about this book in a minute. The first section of the CISC handbook is CSA S1619. The rest is information, design aids, stuff about the different steel sections available. and we'll talk about that throughout the course, and I'll talk more about it in the lab next week. So that's what we're up against, right? As a structural engineer, you have to learn what the NBCC does, what it means, how to use it, and you have to understand S16, what it is, what it does, and how to use it. Now I'm going to start talking about the things that we're going to talk about in this course. This is the course map. I'm going to bring it up every time we come back and finish a topic. We're going to come back to this and see, okay, where are we and where are we going? And so we're going to start by talking about steel structures. We're going to talk about the role of bracing and the role of framing, how steel structures are built. We're going to spend 4 lectures on calculating loads on buildings, basically applying the NBCC and part of S16 to calculate some loads. We'll talk about what that means. We're going to talk about what it means to build with structural steel, and we're going to talk about something called limit states design. And limit states design is essentially a probabilistic framework, and don't get worried by the term probabilistic, but if you took stats, you're probably going to understand, at least at a high level, the philosophy behind limit states design. But limit states design is saying, on average, this is safe enough for the public to use, with a probability we can quantify reasonably well. We're going to talk about the individual steel components. And so some of our braces, when we have loads acting on our building, just like a truss, some of our braces are going to be in tension and compression. We're going to talk about how to design the tension members. We're going to talk about bolted and welded connections, because you can connect things together using welds or bolts, and we're going to talk about the implications of doing so on the strength. We're going to talk about compression members. Everyone should remember Euler's buckling load. We're going to see that again in this course, and we're going to see how we modify that for practical design purposes. Primarily, compression members tend to be some of the braces, but for the most part, we're going to talk about the columns in our building. They're the things that are really under compression, holding all the weight of the floors up in the building, and so we're going to talk about those types of elements. Flexural members, and by that I mean beams. We're going to talk about the primary beams, which are the joists that carry the floor. We're going to talk about the secondary beams, they're the girders that carry the joists. And we're going to talk about the different limit states, so to speak, or the different ways that beams can fail and how we design them so that they don't fail that way. Finally, we're going to look at combined loading, what the combined effects are, and then the rest of the stuff, advanced steel systems, advanced topics, and connection design is going to be handled in the follow-up course if you choose to take that. Okay? I want to whip through a couple things quickly. When we're talking about the design of structures, limit states design, what I mean is we're going to calculate loads using NBCC. We're going to do structural analysis, and in this course, we're going to use a structural analysis software called STAD. We'll talk about that more in the lab on Monday. And then we're just trying to make sure that the strength that we quantify in accordance with S16 doesn't overlap significantly with the load effects so that it's a relatively safe building with a low probability of failure. That's the philosophy that governs the structural design process in Canada. When we talk about tension members, we're going to talk about how things get ripped apart. You can imagine if you got an elastic band, you pull it in tension, eventually it's going to snap. We're going to talk about what that means in the context of steel design. And we're also going to talk about serviceability limit states, which is something that just essentially annoys people. If you have a brace that's fluttering in the wind, it's loud, it's annoying. You want to prevent that if you can. When we talk about compression members, we're going to talk about how things buckle under compressive load. And we're also going to talk about this other serviceability limit state of how things are kept straight and efficient so that the steel fabricators and erectors don't have such a hard time building it in the field and to keep things economical. When we talk about flexural members, we're going to talk about how beams bend or shear too much. We already know how to draw shear and bending moment diagrams. We need to make sure that the beam has a bending moment capacity that's big enough and a shear capacity that's big enough. We also need to make sure it's not going to bend too much. Bouncy floors. Anyone been to the engine library? Bouncy, right? You want to prevent that by addressing the serviceability limit states. We want to make sure beams don't flex too much. And then we're going to talk about at the end, we're going to put all those pieces together because some elements are going to take multiple kinds of loads. Tension with bending or compression with bending, strong and weak axis bending. And we're going to talk about how combining those effects generally makes things worse for a structural member and how we can calculate what the total effects are. So after this course, you should be able to do these things. I already told you what you need to know coming in, but what you need to know going out are these 6 things. You should be able to identify key elements of steel structures like braces, beams, and columns. You should be able to navigate this book, the code and the design aids in it. You should be able to describe the mechanics used to develop some of the expressions. We're going to go back to CE 2023 to talk about how some of these expressions came to be in the handbook You should be able to describe that. You should be able to design the steel components, and this is the big one. Design steel components using S16 to resist the loads prescribed in the National Building Code of Canada, because that's really getting at the heart of what a structural engineer does when it comes to designing a steel frame building. New this year, I've never done this before, but we're going to do it this year. You're going to be able to model and analyze steel components and structures in STAAD and use the functions in STAAD Pro to at least perform a design check on the elements in your model to make sure that they're strong enough to resist the loads that you've got applied to them. And finally, this course is going to be a project-based course where all of the design projects are going to feed into one final project, all focused on the design of a building in the course, and I'll talk about that more on Monday in the lab. Now, how am I going to know whether or not you can accomplish those things? I'm going to apply this assessment structure for the course. Of course, there's always going to be a final exam. I've been told that in the past, making a final exam worth 50% makes people not want to take the course, and they told me if it was 40%, they would have taken it, so that seems like high enough stakes for me, 40% final. In this class, there is no midterm, because I don't like midterms. I don't want to have to grade them. They're a poor metric for student retention and learning in a course. Instead, actually, it's not weekly, but it's lecture quizzes, but the lecture quizzes are going to be due weekly. So every lecture is going to have a few little questions, sort of multiple choice, a quick calculation. They're going to be administered online via D2L. And there will be some issues, but there's a TA dedicated to mitigating those issues, and they'll work with me closely to make sure that things go off relatively well. Every lecture, including this one, okay, I have some, the first quiz is about the course outline. So if you haven't read it yet, you're going to have to read it for quiz 1. The purpose of quiz 1 is to get you familiar with the system, and then all the other quizzes are going to be on the course material, okay? That's going to be worth 20%. That's quite a bit. It's unlimited attempts. You can get 20% easy if you just do the quizzes and make sure that you get them all right, and you can try them over and over again. Ultimately, they will be due 3 at a time once a week. I encourage you to do them after the lecture, but if you want to do them on the weekend, they're going to be due Monday at some time, all right? And of course, the big thing for this course is the project work, and that comprises 4 components. There's the actual assignments that are assigned. Assignments are going to be calculate the gravity loads, calculate the lateral loads, design your tension members, design your compression members, design your beams. That's pretty much what the course is. And those 5 things, 6 things, whatever it is going to feed up into a final design project for which you're going to submit a final submission, which includes a brief report about what design you selected and why and what the limitations are. But along the way, I'm also going to ask you to submit a project proposal. And the reason I do that is twofold. One, every project starts with a proposal. If you're a design consultant, you're going to submit a proposal, say, I'm going to do this by this time for this much. And it's worth 1%. It's just to make sure that you're reading the project requirements. It should be easy. It's graded by a rubric that says if you included all the components and it's professional and free of spelling and grammar mistakes, you get 100%. Same thing for the project update. There's an update report due at midterm, a 1-pager, maybe 2 if you want to push it. And I'm just trying to get you to reflect. How much time am I actually spending on this project? Is it too much? Is it too little? On the project, you should be aiming 4 hours a week, roughly, to work on the project. If you're doing more than that, put it in the update. We're spending way too much time on this. If not, I'm happy with it, and that helps me gauge what the workload is for the course so I can help change it along the way and also in future years try and tweak that to be better across the board. In addition to the report for the final submission, there's going to be some sketches or drawings of the floor plan, the elevations. We'll talk about those in the next couple of lectures. But it's to get you to communicate what the design is in a similar way that an engineer would for a real project. Okay, so the goal is that by the time you're done this course, you should be able to leave and be able to contribute in a meaningful way in a structural office. All right. The absolutely required text. This one. I had some issues with the link. I didn't expect everyone to read the course outline when I actually sent it out the first time. I expected everyone to maybe look at it sometime today. But there's a link to the handbook online. It takes you to the Steel store. It's sold directly by CISC. There's a student discount code. Usually the book's like $400. Student price is $184 plus tax. All right, so relatively cheap. Surely you can find somebody. If you've got the first printing, the 2021 edition, it's not the end of the world. If you got the 11th edition, getting further towards the end of the world, but it's still probably going to be mostly acceptable. We'll talk about some of the differences between the two throughout the time anyway. One of the things CISC told me to tell you is if you get your address wrong and they have to return it to the warehouse for any reason, it's at your cost. So get your address right. Use your student email, the first name dot last name with whatever numbers might be required at umb.ca. If you don't use it, they won't sell it to you. And if you don't use the right address, they'll charge you a chargeback fee. They'll deduct it from the refund. But it's a cheap book, relatively speaking, compared to some other texts, and it's less than half the cost that an industry person, practicing engineer, would pay for the course, for the textbook. I just want to set some expectations around what lecture is going to look like and what labs are going to be. I mean, I'm a very rinse, repeat kind of person. Like, every lecture is going to be the same show, so to speak. I'm going to give you some background and context on why the things that we're talking about that day is important and how it fits into the rest of the course. I'm going to tell you what you need to be able to do by the time that lecture is done, or at least by the time you apply the things you learn in that lecture. For example, today I'll say you should be able to tell me what lecture is going to be like in this course, and that'll be a learning objective, an example of what a learning objective might be, and there are usually 2 or 3 each course. We're going to do some general lecturing stuff. We're going to get you involved doing some polling and some think, pair sharing, where there's going to be a problem, and I want you to think with the person next to you, answer on poll what you think the answer is going to be. And if there's time, I'll do an example of some things, and everyone loves examples. And at the end, just making sure that the stuff we talked about and the stuff we covered is going to contribute to those learning objectives and summarize the content, essentially, for everyone to take forward. In labs, it's going to be a lot less formal. It's just in some room somewhere. I haven't looked for it yet. But we are going to be using STAD Pro. It's free for students if you get a Connect Edition or a Bentley account. It's the way to do that. I'm going to post a document that helps you download and install STAD on your laptops. If you don't have a laptop that you can bring to class or lab to use that, we'll try to make appropriate arrangements. There's also a virtual lab. I think you can access the virtual lab through the computer lab at B level. But labs are going to be dedicated primarily to applying the use of STAD Pro to designing steel members using the things that we talk about in lecture. There are no deliverables for lab. You don't have to be there, but you're going to have to be able to apply STAD on your design project. Okay, I'm going to record the instructional part of the lab. And so if you're not able to participate because you don't have a laptop to make it work, we'll make appropriate arrangements, but it's not essential that I'm not going to ask you to submit your results by the end of the lab, so to speak. But it's going to be hands-on time to learn how to use that in the context of your design project. All right, so that's the course. You're going to see this a lot. You're going to see me a lot. I hope that you enjoy it. Does anybody have any questions about what to expect from CE30?